You may recall that an inverse of a function is when we switch the inputs and the outputs. Well, what happens when we try to take the derivative of one of those inverse functions? We're going to find out right now. So let's take a look at a function, for example, f of x equals x to the third power. And this screencast is not going to go into the details of how to find an inverse, or really too much about what an inverse is, other than to find the definition of what the derivative of an inverse looks like. So if f of x equals x to the third, and we reflect that across the line y equals x, and we switch the inputs and outputs like we're supposed to find an inverse function, we find that the function f of x equals x to the third has an inverse, f inverse of x equals the cube root of x. And for each point on f of x, if we switch the x and the y, the input and the output, we get a corresponding point on f inverse x. For example, point A is at 2, 8 on f of x. If we switch the 2 and the 8, we get 8, 2, which is A prime, the point over here on f inverse of x that's reflected across this line y equals x. And we can do it with other points. Let's just take an easy point to find 1, 1, which actually lies right on the line y equals x and also on f of x and f inverse of x, because 1, 1, if you swap the points, you get the same thing. So to get an idea what the derivative of an inverse function looks like as compared to its parent function, let's look at f of x. And let's just assume that f of x contains 2 points, a point A that is got coordinates of x1, y1, and a point B that has coordinates of x2, y2. So if that's the case, and we flip those coordinates around, f inverse of x, by definition, would have the points y1, x1, and y2, x2. So for example, this is the point 2, 8. So over here at A prime is the point 8, 2. Both points actually are 1, 1. So if we wanted to find the slope of the secant line between A and B, which is indicated by this red dashed line here, the slope of A to B would be y2 minus y1 over x2 minus x1. It would be delta y over delta x. The difference in the y coordinate divided by the difference in the x coordinate, good old algebra 1. If we wanted to extend that with some numbers here to our situation with f of x equals x to the third, the slope of that secant line between A and B is equal to 8 minus 1, the change in the y coordinates, over 2 minus 1, the change in the x coordinates, or 7 over 1, or 7. Well, if the inverse function simply switches the x and y coordinates, then something interesting happens. If I try to find the slope of this segment from A prime to B, it's going to be, if we use these same points, x2 minus x1 over y2 minus y1. In other words, the delta x and the delta y switch places. And so, the slope of this secant line, which is the secant line on the inverse function, is equal to 2 minus 1 over 8 minus 1. It's equal to 1/7. So you can see that the slope of the original function, the parent function, and the slope of the inverse function are reciprocals of each other, which makes sense that since we're switching the y's and the x's, and we have delta y over delta x as our original slope, that it would flip around and become delta x over delta y for the inverse slope. And this concept extends to the derivative. Because as we bring A closer and closer to B, and we bring A prime closer and closer to B as well, the same principle still applies. We're still using the same combination of y and x coordinates, and it's still going to be delta y over delta x for the main function, and delta x over delta y for the inverse function, no matter how close we bring those points together. Even if we bring them infinitely close together, the same principles still apply. So this leads to an interesting conclusion that the graphs of inverse functions have reciprocal slopes to that of their parent functions, and then since the derivative comes from that concept of a slope, the derivative of an inverse function is equal to 1 over the derivative of the parent function, provided 3 things have to be true. First of all, the parent function has to have an inverse. The original function must be continuous, and the original function's derivative cannot equal 0, because if it equals 0, then the derivative of the inverse function fails to exist. So if those three things are true, the inverse function does have a derivative, and it is 1 over the derivative of the parent function.
How did the chicken find the inverse? It reflected the function across y equals x.
So let's use the example that we started with. F of x equals x to the third. The derivative of f of x is f prime of x equals 3x squared. To take the derivative of the inverse function, we just simply take the reciprocal of the derivative of the parent function. So the derivative of the inverse function is equal to 1 over the derivative of the parent function, which is 1 over 3x squared. So without even knowing the inverse function, since I know that the inverse function does exist, the derivative of the inverse function is just going to be 1 over the derivative of the parent function. So for all points on f of x equals x to the third, except where x equals 0, because the denominator goes to 0 here, the derivative of the inverse function is equal to 1 over 3x squared for all x's except at x equals 0. Because at x equals 0, the inverse function is going to have an undefined slope. At x equals 0, the parent function, which you can see here in kind of a blue color, has a 0 slope. So therefore the inverse function, because the y's and x's will be inverted, the inverse function has an undefined slope. So for example, if we wanted to find the instantaneous slope at the point 2, 8, of course the instantaneous slope of the original function will be 3 times 2 squared, or 12. Instantaneous rate of change at 2 of the inverse function is going to be 1 over f prime at 2. In other words, 1 over 3 times 2 squared, which is going to be 1/12. So the slope on the inverse function is going to be 1/12, and indeed the graph of that bears it out. The slope at 2, 8 is given by this red line. It has a slope of, instantaneous slope of 12. 3 times 2 squared. The slope at 8, 2 on the inverse function has a reciprocal slope. Instead of slope at 12, it's a slope of 1 over 12 at that instant. So we've discovered that since the inverse function is created by inverting the inputs and outputs of the original function, the derivative of an inverse function is equal to 1 over the derivative of the parent function, provided it exists and the parent function doesn't have a derivative of 0 at that point.